Today we will begin with a new topic on coastal water level fluctuation. And so to recap about long waves. Long waves propagate through the water column like shallow water waves in the sense that the energy or the water particle circulation occupies the entire water column all the way down to the seabed. And it is in such a way that usually for long wave analysis we can make an approximation that there will be negligible velocity difference from the water surface all the way down to the sea level, so that the velocity can be assumed to be a constant over the entire water column, and such that the hydrostatic pressure distribution dominates the entire water column. So essentially the long wave is a near horizontal flow with negligible vertical velocity component. Pressure distribution is assumed to be hydrostatic, and they have long wavelength, long wave period. Tide is a phenomena due to the celestial movement of the moon about the earth, and also to a lesser extent the movement of the earth about the sun, which causes the periodic rise and fall of the surface water level of the ocean. Now tide has relatively low steepness, which means that the wave height, the tidal height, is so much smaller compared to its wavelength, but it can in some cases have relatively high reflectivity. Tide creates what we call the ebb and the flood current in the coastal region. The ebb current is moving out, whereas the flood current is coming in. The tidal phenomena is so well understood because it is due to the astronomical calculation of the Earth, Moon, and Sun's position, and so it can actually be predicted very accurately, even years in advance. Here we look at the Earth-Moon system. Now, due to the gravitational action of the Moon, as we mentioned, the water on the surface of the ocean will be pulled in the direction of the Moon, whereas the water level in the perpendicular direction, here they will be under low tide. In this direction, the locations will be under high tide. But since the Earth rotates about its own axis 24 hours a day, so you can imagine if we are on a fixed position on the Earth, it will take 24 hours so that you will come back to the same position, and so the position will experience high tide twice a day. Okay, and at the end of the same day it will return to the same position facing the Moon again. But of course, within that 24 hours period, the Moon actually would have moved as well. So the complete lunar cycle is actually 24 hours and 50 minutes. Next, we look at the Earth-Sun system. The Earth orbits about the Sun with a total period of about 365 days. But meanwhile, the Earth also rotates about its own axis 24 hours a day. So any position on the surface of the Earth will experience two high tide and two low tide within a one-day period due to the rotation of the Earth about its own axis. Now, however, we want to take note that the Earth positions in the orbit is not always a fixed distance away from the Sun. It changes. So which means that sometimes the Earth is closer to the Sun, sometimes it is further away from the Sun, and so the effect of the Sun on tide changes throughout the year. We also want to mention that due to the distance of the Sun away from the Earth, the effect of the Sun is actually much lower, less than half of that of the Moon. So all these effect give us the different tidal variation on a daily, monthly, and even annual basis. Instantaneous tidal elevation above a selected datum can be given by this equation, eta. So eta basically is the water level fluctuation above the mean sea level, given by A. So the fluctuating component is given here. It is made up of n number of components. Each one has an amplitude of A and a period T, as well as a phase angle delta. Now the equation itself looks very much like the equation for wave, whereby wave is also made up of multiple components, as we discussed previously in frequency domain analysis. The difference, of course, is that when we talk about short wave, the wave period are in the order of seconds, but when we talk about tides, the period is in the order of hours. So basically, the water level fluctuation is a function of time, and of course it also depends on A, T, and delta. Typically, in order to identify all the different components in the tide, we will need a complete 19-year record of the tidal cycle. However, even if we only have as short as 1 year, it is still possible for us to carry out the decomposition to find out the major tidal components, whereby typically up to 8 major components will be more than enough for us to perform very good tidal prediction, because the rest of the components will have less amplitude, much lower influence on the overall tidal behavior. This figure here shows the different individual tidal constituents and how they combine to produce the daily tidal water level fluctuation that we actually records. Now notice that for each of the components, they will have their sinusoidal component, but the peak of individual constituents are occurring at different time. So that basically is part of the effect of the phase angle between the different constituents. It's of course unlikely that they will all peak at the same time, and even if they are able to peak at the same time, due to the different period, then the subsequent peak will again be offset with respect to one another. So that is how the phase angle affects the final water level fluctuations. So just to mention, if we analyze all the components of the tide, there may be as many as 390 of them. But the most important one are listed here in this table. They are each given a symbol. So as we see here, we have M2, which is main lunar semidiurnal component, S2, which is main solar semidiurnal component, etc. O1 here is the main lunar diurnal component, and P1 is the main solar diurnal component. Semi-diurnal component means the component that repeats itself in the order of 12 hours, and the diurnal component actually refers to the components that repeat itself with a period of approximately 24 hours. Now each of these components will have different strength, so they are given this relative strength. M2 has the largest at 100, and the rest, as we can see, they are lower in terms of the strength, but still significant. So as we go down the list for the rest of the components, then we will find that the relative strength becomes smaller and smaller, which is why even if we ignore the rest of the components, we can still predict the tide reasonably well. This figure here shows the correlation between the tidal water level on the top and the tidal current at the bottom. So if we look at the tidal water level here. This is one complete cycle whereby we have high water here and low water here, whereas at 0 here that should be the mean sea level. Meanwhile, this is the tidal current. We notice that the tidal current is actually out of phase compared to the tidal water level by a phase angle of 90 degree. So as we see here, when the tidal water level is 0, we have maximum velocity. When the tidal water level is maximum, we have 0 velocity. When the tidal water level is 0 again, we have the minimum tidal velocity, and so on. So it's always out of phase by 90 degree. When the current is positive, over here, this is 0 line. So when the current is positive, we have flood tide. But when the current is negative, we have ebb tide. So flood tide is when the tide is flowing into the coastal area, and ebb tide, negative current, is when the tide is flowing out of the coastal area. So obviously the change of direction happens when the velocity change from positive to negative. So we refer to the time when the velocity changes direction, whether from positive to negative or from negative to positive, as the slack. So we refer to this point of time here as the high water slack. That's when the tidal water level has reached the high water level and the velocity is about to change from positive to negative. And this is the low water slack. That's where the tidal water level is at its lowest and the current velocity is about to change from negative to positive.